Good evening everyone, myself Parghoti Biswas from the Department of Computer Science and Engineering. Today, I will be discussing the fascinating topic of clustering in machine learning. Clustering is a fundamental technique in unsupervised learning where the goal is to group similar data points together without any predefined labels. This method helps us uncover hidden patterns and structures within datasets, making it an individual tool in data analysis. Whether we are dealing with customer segmentation, image analysis, or anomaly detection, clustering allows us to make sense of complex data by organizing it into meaningful groups. Now we will move to the next slide that explains what is clustering. Clustering as its core is the process of grouping data points into clusters based on their similarity. The principle is simple. Points within the same cluster share similar characteristics, while those in different clusters are dissimilar. This process is particularly powerful because it doesn't require any prior knowledge of the data. Hence, it's classified as unsupervised learning. By analyzing the inherent features or structures in the data, clustering enables us to discover natural groupings that might not be immediately apparent. We'll move to the third slide that describes about the types of clustering algorithms. There are several clustering algorithms, each with its own strengths and weaknesses, depending on the nature of the dataset. The most commonly used types include partitioning algorithms. These algorithms, like k-means and k-medoids, divide the data into distinct clusters by minimizing the distance between points and their respective clusters centroids. Then comes hierarchical algorithms. These build a tree of clusters which can either be agglomerative, merging smaller clusters into larger ones, or divisive, that is splitting a larger cluster into smaller ones. Then comes density based algorithms. Algorithms like DVScan find clusters based on the density of points in a region, making them ideal for identifying clusters of irregular shapes and handling noise in the data. Model-based algorithms. Gaussian mixture models, for example, assume that the data is generated from a mixture of several Gaussian distributions and the task is to identify those distributions. Then the fourth slide is generally describe about um, one of the most popular clustering algorithms, that is k-means. K-means aims to partition data into k distinct clusters, where each data point belongs to the cluster with the nearest mean. The process involves four key steps: initializing, randomly select k initial centroids, then assignment, assign each data point to the nearest centroid forming clusters, then update, calculate the new centroids at the mean of the point in each cluster, then repeat the assignment and update steps until the centroids stabilize, meaning they no longer change significantly. K-means is efficient and works well with large datasets, but it assumes that the clusters are spherical and of equal size, which might not always be the case. Then we'll move to the fifth one that describes about hierarchical clustering. Unlike k-means, creates a tree of clusters which can either be agglomerative or divisive. In agglomerative clustering, each data point starts as its own cluster and the algorithm iteratively merges the closest clusters until only one remains. In divisive clustering, the process starts with one large cluster containing all the data points, which is then split recursively into smaller clusters. This method is particularly useful when the data has a nested structure or when we want to visualize the relationship between clusters. Then comes the DVScan or density-based spatial clustering of applications with noise. It's a powerful clustering algorithm that identifies clusters based on the density of data point in a region. It classifies points as either core points, border points, or noise points. Core points have a high density of neighboring points. Border points are in the neighborhood of core points but have fewer neighbors. And noise points are isolated from others. DBScan is especially effective for identifying clusters of arbitrary shape and handling noise, making it ideal for complex datasets. Then we'll move to the next slide that describes about the choosing the right clustering algorithm. The choice of a clustering algorithm depends on the characteristics of the dataset. For instance, k-means works well with large dataset and well-separated clusters, while hierarchical clustering is better suited for understanding hierarchical relationships and identifying clusters of various sizes. DBSCAN is based for datasets with varying densities and irregular cluster shapes. To determine the most suitable algorithm, it is essential to experiment with different methods and evaluate their performance using appropriate matrices or metrics. Then we'll move to the next slide, that evaluating cluster performance. Evaluating the performance of clustering algorithm is crucial to ensure the quality of the clusters produced. Several metrics are commonly used. That's Silhouette score measures how similar a data point is to its own cluster compared to other clusters. Davis Baldwin index evaluates the average similarity ratio of each cluster with the cluster that is most similar to it. Kalinske-Harab's index measures the ratio of between cluster variants to within cluster variants, with higher values indicating better defined clusters. These metrics help us fine-tune the clustering process and choose the best algorithm for our specific task. Then applications of clustering. Clustering has widespread application across various domains. In marketing, it is used for clustering segmentation, grouping customers based on their buying habits and demographics to tailor marketing strategies. In computer vision, image segmentation divides an image into distinct regions based on object characteristics, which is crucial for tasks like object recognition and scene understanding. Clustering also plays a vital role in document clustering, anomaly detection, and social network analysis, highlighting its versatility and importance in modern data analysis. Now, we will move to the next slide. To conclude, clustering is a powerful technique in unsupervised learning that allows us to uncover hidden patterns and structures in data. By understanding and applying various clustering algorithms, we can solve a wide range of problems across different domains. Whether it's segmenting customers, analyzing images, or detecting anomalies, clustering provides us with the tools to make sense of complex data sets, ultimately driving better decision making and insights. With this, I would like to end my presentation. Thank you.